Thank you for viewing Part 2 of the Silicon Labs video presentation on clock jitter and PLLs. In Part 1, we discussed clock jitter, jitter classifications, and jitter measurement. Part 2 will focus on jitter characteristics as applied to PLLs and clock buffers. What is a phase lock loop? A phase lock loop, or PLL, is a feedback system that locks a generated output signal's phase to an input reference signal phase. For the purposes of this presentation, the signals of interest are clocks. When the input and output phases are aligned in a steady-state condition, the PLL is said to be locked. When it comes to clocks, PLLs are most commonly used to 1. Translate one frequency to another. This includes clock multiplication and/or division. 2. Attenuate jitter by using specific frequency response low-pass filter to filter phase detector output before driving the VCO. Or 3. A combination of frequency translation and jitter attenuation. 3 important PLL characteristics with respect to jitter are jitter transfer. This is the amount of jitter transferred from input clock to output clock. The jitter transfer function gives the amount of jitter attenuation that will occur at a particular offset frequency. It is strongly affected by the loop bandwidth of the PLL, which is strongly affected by the PLL's low-pass loop filter. Another important characteristic is jitter generation. This is the amount of jitter generated by the PLL itself independent of the input clock's jitter. It is the amount of jitter at the output of the PLL when a zero jitter clock is applied to its input. Jitter generation value varies significantly with the frequency offset from the carrier. Typically, jitter generation falls off as the offset value gets larger, although this is not always the case. The jitter generation curve of a PLL establishes its noise floor, and the PLL's performance at any given offset frequency will never be better than its jitter generation value at that particular offset frequency. Another important characteristic is jitter tolerance. This is the maximum amount of jitter on the input clock that can be tracked by the PLL without losing lock. Jitter over this amount may cause the PLL to fall out of lock. Let's take a closer look at one application of a PLL, clock jitter attenuation. Jitter attenuation is an example of exploiting the jitter transfer characteristic of a PLL. A PLL's response to jitter can be characterized as low pass due to the use of a low pass filter to filter the phase detector output. This low pass filter, in part, governs the VCO's response to deviations in clock frequency and phase. That is, input clock jitter at an offset frequency that is above the loop bandwidth cutoff frequency will be attenuated by the PLL, and jitter that is below the loop bandwidth cutoff frequency will not be attenuated and will therefore pass through the PLL. For this reason, the lowest loop bandwidth value is desired in many circumstances. However, low loop bandwidth comes at a price, because the lower the loop bandwidth of a PLL, the slower it is to respond to changes at its input. At some point, very slow response time becomes a significant problem. One interesting question to consider with jitter attenuators is there a minimum jitter level below which it is not possible to go lower? The answer is yes. Due to the jitter generation characteristic of PLLs, there is a minimum output jitter. Even with a theoretical no jitter input clock, a PLL will still exhibit some minimal amount of output jitter. This minimum output jitter represents the noise floor of the PLL output. This is a plot of PLL jitter attenuation when using a 100 Hz low-pass loop filter. Note that the jitter attenuation at 100 Hz is minus 3 dB, which would be expected from a low-pass filter with a cutoff frequency of 100 Hz. The key point is the amount of jitter attenuation is directly correlated to the loop filter bandwidth. Next, let's examine phase noise plots created with a low noise clock input signal to see how the loop bandwidth affects jitter attenuation. These plots show the jitter of an RF generator with 622.08 MHz sine wave carrier without any modulation. This is shown in the blue trace. And this is connected to the clock input of an SI 5324 jitter attenuating PLL with a loop bandwidth of 7 Hz, and this is shown in the red trace. And it's also connected to an SI 5326 jitter attenuation PLL with a loop bandwidth of 120 Hz, shown in the green trace. The output jitter of the RF generator and the two PLLs are superimposed upon one another. The red curve, which is the lowest bandwidth jitter attenuator, has the best phase noise performance close to the 622.08 MHz carrier. For larger offset frequencies towards the right side of the plot, after the crossover arrow, the RF generator surpasses the performance of both PLLs. At these larger offset frequencies, the phase noise for the red and green PLL curves are purely jitter generation, because the phase noise at the PLL clock inputs is lower than the phase noise of the PLL output. That is, the phase noise at the PLL output is due to the PLLs and not their input clocks. Close to the carrier, the green and red curves show that the RF generator's phase noise is being attenuated by both PLLs, though a greater degree by the red PLL. Accordingly, for points that are at the right tip of the crossover arrow, jitter generation is being displayed. The points to the left of the tip of the crossover arrow show jitter attenuation. This plot shows the same configuration, but with jitter on the RF generator's 622.08 MHz output due to sine wave FM modulation at 500 Hz. This modulated output is connected to the clock inputs of the SI 5324 PLL, the loop bandwidth of 7 Hz, and the SI 5326 PLL, the loop bandwidth of 120 Hz. The output jitter of the RF generator and the two PLLs are superimposed upon one another. The plot shows the FM modulation at 500 Hz intervals. Notice that the prominent spur at 500 Hz is only somewhat attenuated by the SI 5326 with its loop bandwidth of 120 Hz, but is significantly attenuated by the SI 5324 with its loop bandwidth at 7 Hz. The increase in jitter attenuation at low offset frequencies is due to the lower loop bandwidth. This plot shows the same configuration, but with RF input signal jitter at 10 kHz. The jitter attenuation due to the SI 5324 and the SI 5326 is roughly the same because 10 kHz is much larger than both of the loop filter bandwidth values. The jitter transfer curves for the SI 5324 and the SI 5326 jitter attenuating clocks are shown in this plot, along with the jitter transfer of an SI 5338 clock generator, which is a wideband PLL with a loop bandwidth of over 1 MHz. As such, the 5338 will attenuate very little jitter. As a consequence, if a wideband PLL, that is a PLL with a very large loop bandwidth, needs to have low output jitter, it must be driven by a low jitter clock source. It is important to understand that the selection of an appropriate loop bandwidth value is application dependent. If the clock source already has low jitter, then a higher loop bandwidth might be suitable. However, if the input clock has significant jitter, a lower loop bandwidth should be considered. In these situations, the system-level jitter requirements need to be considered. Some networking standards establish a lower limit to the jitter offset frequency that needs to be taken into account, and therefore jitter below a certain offset frequency is either not considered or discounted. Examples of such standards include SONET, Optical Transport Networking, and Ethernet. However, some standards require loop bandwidth values as low as 0.1 Hz, for example, synchronous Ethernet. Video networks typically care about jitter that is down to 30 Hz because of video frame rates, which call for a loop bandwidth below 10 Hz. Jitter tolerance is the amount of peak-to-peak jitter that can be applied to a PLL before it loses the ability to lock or maintain lock with an incoming clock signal. The jitter tolerance is affected by both the loop bandwidth and the offset frequency. Clearly, the jitter tolerance for offset frequencies below the loop bandwidth of a PLL will be high because the PLL simply passes the jitter through with little attenuation. Similarly, a PLL with a low loop bandwidth will have less tolerance for jitter than a wideband PLL. A typical jitter tolerance curve is shown in this graph, with bandwidth referring to the loop bandwidth of the PLL. As the graph shows, there is a break in the jitter tolerance curve at the loop bandwidth. Once a low jitter clock source has been created, it is often necessary to send this clock source to a number of different destinations. A fan-out buffer is usually used to perform this function, which leaves the designer with the question of how much jitter will be added by the fan-out buffer. Two devices want a clock source with jitter, J1, that is driving a fan-out buffer with additive jitter of J2. What will the final output total jitter be? Mathematically, the output jitter can be anywhere from J1 plus J2 to J1 minus J2 if the jitter is uncorrelated. In other words, it is possible for the two jitter sources to either constructively add or to subtract from one another. It depends on whether J1 and J2 are correlated. A simplifying assumption that is often made is that J1 and J2 are not correlated. As discussed earlier, this would be a very good assumption if both J1 and J2 were comprised of purely random jitter. However, as the amount of correlated jitter increases, this becomes a less valid assumption. If J1 and J2 are truly uncorrelated, then the total output jitter can be estimated from the root sum square equation shown. If the jitter at both the output and input of clock buffer J2 is measured, then J2's additive jitter is defined as the root mean squared difference between J2's input and output jitter. This is shown in the equation that solves for J2 additive jitter. Consider the following example, which uses two SI5330 4-to-1 fan-out buffers, each with an additive jitter specification of 0.15 picoseconds when integrated from 12 kHz to 20 MHz. What would you expect from the phase noise plot of this arrangement? Let's take a look. Looking at the plot, as expected, the lowest jitter is without any fan-out buffer, and adding a buffer increases the jitter. However, adding a second buffer does not incrementally increase the jitter as much as adding the first buffer. This is because of the square root of sum squared value that is associated with uncorrelated random jitter. Let's look at this data in tabular form. The table below the plot shows corresponding RMS jitter values, showing both the measured and calculated values. The red values are calculated from the root sum squared, while the black values are all measured. Notice that the root sum squared values are close to their corresponding measured values, but the root sum squared values are nonetheless both slightly less than the measured values. This indicates that some of the noise is indeed correlated. Remember the opening question, why is jitter important? This presentation has provided an overview of relevant clock jitter issues for many modern system designs. Jitter and phase noise are increasingly a concern for many different and diverse types of electronic systems. Because the applications of these systems are so varied, the specific requirements and areas of concern for each individual application can be quite different. Accordingly, it is important to be aware of the different ways of defining, specifying, and measuring jitter and phase noise, as well as knowing which are relevant to the particular application at hand. To this end, the developer should understand and recognize the capabilities and limitations of the various types of test equipment. Even though such equipment tends to be very expensive, it is often not easy to properly interpret the results and their significance in a given situation. Hopefully, you found this presentation helpful in answering the question of why jitter is important. Don't forget to please stop by our website at www.jitter www.scilabs.com/timing for more information. From everyone at the Silicon Labs timing team, thank you for watching.